We always feel watched by the camera.
Ah, okay, wow.
Maybe that is not the right people for the camera to be pointing.
Well, okay, so let's get started today. It's my great pleasure to have Richard Tsai, agreed to give a talk from the University of Texas at Austin, and he's going to talk about numerical wave propagation aided by deep learning.
Thank you for the invitation. I realize that this talk might be, kind of off-center from the main theme of this conference, but since I'm solving hyperbolic equations, and I hope that at least you can get something out of it. And I also realize that I'm the one obstacle between you and the cake. So I will try very hard to be on time. So this is a project together with one of my former students who's now doing a postdoc in Basel. And it's a project supported by National Science Foundation and Research Office of Science Foundation. So we are, one of my research focus was on developing multiscale computational algorithms. And in particular, multiscale problems involving hyperbolic operators and oscillatory solutions. And you can say that a branch of this type of research involves numerical homogenizations, where so this talk is related to solving a linear wave equation that can be used to model acoustic wave propagation. So in this particular setup, the wave speed would be highly oscillatory in space, and it also supports solutions that has very large oscillations. Now, we're aiming at, so of course, the game of numerical normalization has been played, and there are a lot of experts doing that. So what we are aiming at is to think about what's next. So pushing the frontier of multiscale algorithms. And typically, so here in the first line, you see a kind of a type of multiscale algorithms that somehow aims at extracting an effective model based on some kind of very localized numerical calculations. So you make in the context of this work, it will be you solve some wave equation with some suitable initial conditions in some suitably small neighborhood, and for some time, for some small amount of time, and then you see how the wave field changes, and from this you try to derive what would be a kind of a model, a PDE, involving operator that does not depend on the small scales. Because the idea is that when you can discretize this homogenized model or this coarse grained model without the need to resolve all the oscillations, and therefore you can have a cheaper prediction of this kind of wave phenomena. So therefore you have capital F here denoted by, which is used to denote by some kind of effective model that we try to define using online computation data. So the online computation data will be denoted here by D, like this. And then it might be in an iterative form. So the solution that you try to construct will come with a superscript that denotes the iterations that's going on. Cap U denotes the effective solutions that you get, removing the smaller oscillations in oscillatory components in it. And the F, lowercase f here would then denote, the full-scale wave equation with highly oscillatory coefficients, very high contrast, whatever nasty things that you have, and you believe that this smaller lowercase f would provide a reasonable description for the phenomena that you're interested in. Now, the solution for this full-scale problem is denoted here by U, as I mentioned earlier, we typically want to solve this this fine-scale solution model in a smaller domain, spatial and time domain, because otherwise it's too costly to compute. So therefore, you need to equip it with certain suitable boundary conditions as well as initial conditions. If you're familiar with homogenization, this is so. You need to set out suitable boundary conditions, and these kind of suitable boundary conditions will be, denoted here by as the data, and this data depends on the core solutions cap U that you're being computed. So in this way, you have a coupled system where you have this cat F, which is your effective system defined globally in the computational domain of interest. And then you have smaller, in a smaller domain, you have this full-scale problems where certain setup in the problems, such as boundary conditions, initial conditions, were dependent, again, by the coarse scale models. So this could be used to describe the setup of numerical homogenization very well. But now we're, as I mentioned earlier, we're thinking about what's next. So you can say, so what would be next? It will be something like in the context of homogenization, you don't have enough scale separation in the problem. So then, your homogeneous solution, is this concept of homogenizing and pushing the epsilon or this small scale, a parameter denoting the small scale to 0 and still derive something that reasonably approximate phenomena kind of fails. So this will be one situation. And another type of situation, I mostly deal with time domain problems. So, the other situation that I would like to mention here is like, for example, you have oscillatory systems with a lot of oscillations, and sometimes these oscillations come into resonance. And then after a while, and then these oscillations will get out of the resonances. And the implication is this: when you are thinking about highly oscillatory evolution problems, usually one way to get rid of the dependence of this oscillation, this very fast oscillation, is to kind of apply some kind of averaging theory, which just tells you that when the oscillation is very, the frequency of the oscillation is very fast, then you can separate this fast scale related to the oscillation, and then the slow, the background, which is something that goes on in a much slower time scale. These can be separated when the frequency is high enough. Now, in which space you want to make this kind of average? When systems are in resonance and out of resonance, if you think about Hamiltonian system, you need to average over different, the invariant tori of different dimensions. And the passage from non-resonant modes to resonant modes is something that you don't have separation in this kind of oscillatory kind of scales. So, which means that if you are faced with this kind of problem, then classical multiscale method would not be adequate. Okay, so this is what we're thinking. So these are the situations that we aim at. And of course, in this era, due to the popularity of deep learning strategy, so we're kind of tempted to say, so what can deep learning do for us, in particular, in this kind of facing this more challenging multiscale computation setup? Okay, so so I'll give you a concrete example involving high frequency propagation like this. So so here what you see is computational domain, and the color of this in the background denotes the wave speed. Okay, so you have essentially piecewise constant wave speed. Wave propagates at different speed. And if we set up an initial condition, so here it denotes the energy of the initial condition, and it's highly oscillatory with respect to the length scale, physical length scale of the problem that you're interested in. So this is a Gaussian pulse modulated by some plane wave, right? And it's set up so that it's going to propagate downwards. So in this particular setup, if the background wave field is smooth, then and you consider the frequency here or the wave number here to be very high, then you can set up a system of ODEs to predict how this wave energy will propagate into the media at later time. And this set of ODEs, so there are multiple versions of this. One version is called Gaussian beams, and I think some people, including myself, would try to use Gaussian beam to solve linear Schrödinger equation in high frequency setup. Okay. So now it predicts that. So in this particular case, you solve instead of a PDE, you solve a system of ODE. And the center line here denotes the trajectory of that's predicted by the ODE. And basically, the ODE predicts how the energy and the shape of your wave field will be around this trajectory, this path array. So after some time, this will be the energy that's being computed, being modeled by your Gaussian beam system. But if instead you discretize this linear wave equation, with a very high resolution. What you're gonna find out, this is a, kind of a snapshots, multiple snapshots overlaid together like that. So you see that the energy first come down here, and due to the discontinuity, there's some interaction, there's some kind of refraction and transmission going on. And then most of the energy will remain somewhat similar to the middle part, but then there's a group of energy that's being, kind of scattered and arrive over here at the final time, like that. So why is that? Well, this is because in the ansatz of this Gaussian beam, when you derive your multiscale model, which here is called Gaussian beam, the ansatz failed as the group of energy is grazing through a discontinuity or through a region where the wave speed has very high gradient. Okay. So and then you will see that we would like to have develop a systematic way, computational method in a systematic way, so that you don't need to worry about when this model would fail. But with assumptions that when it doesn't fail, it's still a reasonably good model. And of course, it's tempting to think about applying whatever you try to develop, or you aim at what you want to develop for such kind of scenarios. This is one of the kind of test problems used in the industry to compare numerical algorithms. Right? This is a physical domain, right? So this is in meters. The units are in meters, and this is the wave speed. I think probably seconds per meters per second or something like that. I'm not so sure. But, so the point here is to see that the configuration of this wave field, there's a lot of discontinuity, right? There's also the gap between the maximum and the minimum is relatively large. So it is quite a challenging problem to be. Of course, that's why people try to use it. Now, in this talk, what you will see is that there is this numerical solver, which is an accurate one that resolves everything, and you believe that it gives you a reasonably good model. And we're going to say that it advances a given wave field to a later time, and the gap in time of propagation is denoted here by delta t star. Okay, and then there's this coarse solver or this homogenized solver, whatever you call it. When the problem is nice enough, then it provides a reasonably accurate approximation to the phenomenon, but it may fail unpredictably. Okay, unpredictably based on the solution, like that. And the focus of this talk will be concentrating on defining or constructing a correction operator, so that the input of this operator will be what is computed by your coarse computation, and the output hopefully will be as close to the idealized fine solver or the exact solution to your PDE, as close to that as possible. So that's the objective. We want to construct such kind of correction. And then later on, maybe in a split minute or so, we will see some kind of fixed point iteration that couples these the correction operator together with the different components, the coarse solutions and fine solutions in an iteration, so that your computation is improved as the K iteration goes. Okay, so to set the things a little bit more on the concrete footing. So this is the simple linear equations that we're dealing with for any fixed wave speed denoted here by C epsilon. This is a linear problem, but the solution itself, U itself, depends on nonlinear. It depends nonlinearly on the wave speed itself. So we're gonna just say that we discretize this problem in a unit square. With say periodic boundary condition or absorbing boundary conditions using uniform partition grid. One is very costly and highly accurate, so you don't want to do it globally in this in this domain all at once. And there's something on the coarser grid you can do some typical finite difference schemes on it, and this is denoted here by G sub delta T star. This is the coarse scale operator. They live on different grid, ideally. So they need to communicate. So you need to map one grid function of different resolution to another grid function of final resolution, etc. So these two operators are necessary, but most of the time we'll ignore them because they don't present any. So in the language of say multi-grid, this is called prolongation. One is called prolongation, which means you want to map a coarse grid into a interpolation, essentially. And if you want to map a fine grid onto a coarse grid, then this is called a restriction operator. In machine learning community, this will be called downsampling. One is called upsampling, and the other one is downsampling. So for convenience, this wave equation is the second order in time equations. So actually, what we're going to deal with is a vector that's u and u sub t, the time derivative, like that. And then we're just going to denote this vector here as by boldface u, and then it will be, whenever you see it, it will be a function that's defined on the final. Okay. Now, so of course, the first question that we want to ask is, what do you want to correct? Right, so I give you some examples, but what more precisely do you want to correct? Okay, so then we start to think, okay, we can say a little bit more about this when C is smooth. So let's consider the smoothest C, which is constant. Okay, even in this situation, there's something to be corrected. So so let's say that if we plug in the plane wave into the wave equation, then you will see that the omega and C over here has to satisfy up to a sign a linear relation, right? So this is called the dispersion relation. So that tells you how plane wave should be propagated. If you have if you have exact solution. Now, if you plug this plane wave into the say second order central difference scheme that's commonly used in discretizing this wave equation, what you will find out is that you will have a nonlinear dispersion relation. Okay, and to leading order, you get the linear part similar to this, but then you have some perturbations going on, and the effect of perturbation is worse when say the wave number is increasing, C is increasing like that. And this tells you that, of course, there is a balance. There's a limit if you fix a delta t, how many waves you can see, etc. And together, they give you this thing. So this is a real computation. And you see, we set up a grid on this in this strip, and initial condition, which is a pulse denoted here by blue curve, set it up, UT set it up so that it's propagating to the right. After some time, ideally, it should arrive at the location and configuration denoted here by the red dashed line. But if you plug it into this numerical scheme, what you see is this. So different components, Fourier components of this pulse over here travels at different speed. And this is just, a graphical illustration of this. Okay. So in other words, our correction operator, what does it need to do? It needs to correct this orange curve, map this orange curve to some function as close to the red dash curve as possible. Okay. Now, this is even more, right? Because we think about, so now the next step is we think about, piecewise constant wave media where you need to think about scattering of wave energies. So we set up an initial pulse like this, and it's propagating, in these directions like that. So this is your expensive, fully resolved solutions like that. And this is the core solution that you get. Again, you see this kind of trailing of different oscillations, different components. And then you also see, some people call it the delayed arrival of wave energy because your numerical dispersion is not up there yet. So this is an example where we can see to test the effect of scattering and this kind of arrival time. And again, our correction operator should take this as an input, right? And map it to something like that. So it should push all the waves in the right speed. And then if the refraction is wrong, then it has to correct the angles. So these lines here are just tools to help you notice, compare, how the wave should propagate. Okay, so So our idea is to construct this correction operator here. We just loosely denote it by theta through optimization. So how do we optimize? Well, so ideally, this theta should really be this operator, right? You take your core solution, you take it back, and then you do it in fine grid operation. But this is not practical, right? And then you don't need to worry about this. So of course, the idea is whether this operator over here has some kind of structure that one can exploit. So we can compute this. We can construct an approximation to this operator that does not require as much computational resources as possible. So in a very abstract way, we want to construct theta in certain class of functions in certain space B, so that it maps the coarse solutions to the fine solutions as best as you can in certain energy, in certain metric or norm for a class of wave field, loosely denoted here by H. It's very abstract. I mean, it's very non-concrete. But this is the objective. And hopefully, I don't think I have crystal clear information for each one of these, but at least it gives you a map of what you're looking for. Okay. So now the first thing is that because of the linearity in the problems, we're gonna just use the wave energy semi-norm for comparison. Okay. So and if you analyze, this is actually non-dimensional. So it scales nicely when you refine it with a set up. And the class of functions or the space in which we want to look for this correction operator will be, this correction operator in this talk will be a trained neural network. Okay? And then it will be defined in this way where we first, since we want to use the wave energy semi-norm, so we first map the wave field UT into gradient U and the weighted U sub T, the momentum. And this H sub W denotes the neural network that I'm gonna tell you about. And then after that, you will map back by some super inverse and map it back to the wave field like that. Okay. Now, so this is another view, right? So we started out by saying that we want to find some operator theta in a certain space, minimizing the difference between the coarse and fine scale in the wave energy semi-norm for a class of wave field and for a class of wave speed. Now, the class of wave field, strictly speaking, the class of wave field and the class of wave speed, actually they're highly correlated because even when you start out with a Gaussian pulse, that's the initial conditions, you set it into different seeds, different wave media, you will have different wave fields, right? And it's impractical to say that I'm gonna just minimize this for the entire class of I don't know, continuous functions. It's not practical computation. So then we say, okay, so you will see how we reduce the complexity in this case. But so this is the operator, and I just briefly describe how this operator will take the form. In the middle here is the neural network, and then this lambda is just mapping to the gradient weight properly weighted, and this is the pseudo inverse. And this objective will be then relaxed a little bit further in the supervised learning setup, involving that allows one to consider a deep learning approach, where now you minimize this. So the class of functions that we're thinking about will be defined by the neural network architecture, as well as the number of trainable parameters that one used in defining such kind of neural networks. So this is denoted here roughly by n sub m, denoting that you have so many trainable parameters. And then this guy over here, together with the desire to minimize this guy for the whole class of wave field, is translated in a way over here, is modeled over here by just the empirical mean of data. Around the data, right? So xi and yi are the labeled data sets coming from certain distribution. So in this particular setup, xi will be related to the solutions, or what we call the energy components of the solutions computed by your coarse numerical methods. And then the label part, so people in the field call this Y, it is called label. So Y is computed, is your find, the solution, fully resolved solution that's too costly for you to compute online. And you just want to minimize this. This is your like that. Is that clear? So that's what we want to do. Right. So now the question is, so here I said I don't really know. I don't think that, for example, to have a class of what would be a reasonable class of wave field that we should consider, because they depend also on the class of wave speed that you want to consider the propagation. Now, this question here becomes the question of what is the distribution from which you want to get the training example. So in this particular case, this is not the set of data points that you go to the field and gather. This is you do it, on your computer. You generate training examples. So how what kind of distribution should you sample in order to get you be able to define a neural network that does this job well? That's what you want to do well. So this is coming up. So first about the function class, right? So what we decided is to use a modification of what people call a UNet. So if you haven't seen neural network, so now is your chance. It is a type of functions that's defined by very simple operations, basically defined by compositions of affine transform together with certain composition with certain nonlinear functions, like a sigmoid, a hyperbolic tangent, etc. And then you just repeat the same procedure multiple times, and then you will get, that's the deep part, the composition of this kind of construction several times. So then you get a deep neural network. So this one, and here, W and B, W would be a matrix. So affine transform, as I mentioned, and B would be a vector. And then this will be a component by component application of a sum function G. People, in the community, people call it activation function. This is a graphical picture of depiction of what's going on. The class of functions that we want to use. It's multi-resolution because you gradually reduce the number of components, which somehow correspond to your spatial resolution. Structurally speaking, it resembles, if you're familiar with multigrid, it resembles one beat cycle of a multigrid method, where the convolutions are the actions of certain convolutions of certain kernels are denoted here between the blue layers, like that. Okay. Now, this is a diagram of what's going on. So you start out with this wave that's being computed by the core solutions. You map it into what we call the energy components, the gradient, spatial gradient of U, and the weighted time derivative of the wave field, represented here in color, RGB. So it looks like this. You pass in through this operator, which is defined by this guy. Magically, just composition of affine transform nonlinear thing, nonlinear function, and then affine transform. That. And this guy takes input of this guy of the wave field, as well as the type of wave speed that you want to propagate this energy for delta t star amount of time. It returns this guy, and then you go back to, this is the process. This is, hopefully, this wave field will be much closer to that being computed by the accurate fine solver. How do you generate training data? What is the distribution of training data that we want to do? Well, in the paper, in this project, what we do is we get these two sample media. This is called Marmusi, and this is called BP, probably related to some task database from British Petroleum. It's very large. You do a random crop of random rotations of subdomains of these task media, map it into a reference square. Okay, so that would be, each one of these blocks would be one sample of your wave field. Okay, so this to describe what type of wave fields are we sampling. We do some sort of uniforming rate, rotation, and the scale boxes, stuff like that. And afterwards, it's a question of sampling the wave field coming, that propagates through such kind of sample media, right? It's highly correlated, it's causal because, it's wave equation we're talking about. So on the horizontal axis, the samples denotes how we sample the wave speed as well as a class of initial conditions. Okay, and then you have to bite the bullet and use some larger computer, spend a few nights computing the solutions, propagating the wave, these initial conditions into the domain, and see how the fine solution and how the coarse solution differ in the form of just recording how they're different, right? Sorry. And this will be recorded here as, again, as a pair of functions, right? So the blue one is your x, and then the red one is your y, the label part, right? And this defines the joint distribution. You can see that there's without, really involving the PDE, solving the PDEs that you want to solve later on more effectively. There's no way to generate this because each one of this is like the curve. It's strongly causal. There's no dissipation, so you cannot say that these eventually will converge to some kind of manifold that's fixed. So now we know, in theory, we know what kind of training data we do. So we kind of have an idea what kind of wave field we're trying to optimize this correction operator, right? And so it's one thing that you say, okay, I use some kind of optimization method to solve this optimization problem and define this correction operator. And I know how small it is from whatever data points that I have generated from my training example. It's another thing to really apply it to somewhere else, right? By the way, these things are, I haven't shown you the results. Okay, so now it's time to do the diagnostic. So this is what happens with that particular training data set that I described quickly. Right? So again, this is the wave speed, this is the initial wave energy. This is the fine solution, this is the coarse solution. And we compare this two different, neural network of two different complexity essentially. So this is our analogy to say grid refinements when we do numerical computation in classical setup. So this involves more parameters, and this is a 3-level involves fewer parameters. And you see how this guy is being corrected like that. Further, you see that with a finer grid, right, a larger model, you resolve these fine details better than this guy. Okay, like that. Okay, and this is the scattering situation. So we set up following the motivation, one of the motivating slides here. This is the wave speed, and you have some kind of scatter in the middle. And here you even have a corner, right? So you will have some kind of problems like this. Initial pulse is located at the location denoted here by X. This is the coarse wave field. This is the fine solution. And here, we see the error from the coarse solutions, and this is after using a 3-level JNet to correct. That's the residual or the error. Okay. So you see a lot of these things are corrected. It's not perfect, but at least visually we see a pretty good improvement. And this is so these two examples do not exist in the training data set. Okay, now the next step is to improve with further. So these training, right? This correction operator that we have constructed is you spend a few nights on the cluster, and then you get that set of matrices and weights, and that's your correction operator. That's operator constructed from, I say, offline data, where you can afford to spend more time, more exposed to do. Now, when you try to use it, as we mentioned, when you send a wave here, because this wave speed is not in the training data set, so most likely you will see some wave field that may be, may deviate from the distribution that you sample in some way far. Right? So there should be another way to further improve the effect, the accuracy of the correction algorithm. So this is what comes in. So the idea is we're going to use a French invention. We're going to use a French invention which is called parareal iterations. It was formulated by actually the senior Jacques Louis-Lyons and Tourinichi and Madej around 2000. And the idea is to allow time parallelization of an evolution problem. Okay. So, but anyway, we do a modification of that, and it takes this kind of form. You can just think of it as a particular fixed point iterations. The iterations is denoted here by K, and theta here is our correction operator, and you know all the ingredients. So this is a further correction that is that is imposed through this thing, right? So at iteration K plus 1, this is of course computation, and which is improved by your neural network, but you don't think it's enough, so you add some kind of correction, and this correction is like a constant extension in some sense of you add the difference between the fine solver and the corrected coarse solver back from the previous iteration. You add it back, you add the difference back, and then you just iterate on this. And the idea is that hopefully with very few K, right? The solution here would be much closer to what you really want, much closer to this guy. Okay. This iteration itself has a lot of problems. Without theta, has a lot of problems or problems with no dissipations. But that's another talk. So, but but if you think about this, if you look at this structure over here, this K is the previous iterations. So you allow your you allow to the computation of this very costly fine solver in a parallel fashion. We can farm it out for different time segments. So that's where the time parallelization comes. And this correction itself, right? This could this is expensive. This guy here is the online, what I call online data, because the data exists only as you compute, as you simulate with on the same time. So this is online data. Now, I have to show you the effect, right? So if you follow me from the upper left to the lower right, so this is the core solution, right? This is the input that we try to correct. We apply the neural network. First time, you see that things seems to be in place, but there's still some kind of trailing oscillations going on. Second iteration, you see the structure here becomes sharper. Third iteration, etc. And this is just for visual comparison. This is the final solution. Of course, that's not where we should just stop. We study further these four class media, which do not exist in the training example, just to see, kind of see whether we can find the limit of the operator structure. But the other thing that I would like to mention to you is the importance of this training data set. I describe a rough idea of how you need to generate your training data. Roughly, you sample the wave speed, you sample the initial conditions of interest, and then you propagate. But if you want to use it in this kind of setup, this kind of iterative scheme provides another dynamics. So they chop up. So this operations over here would generate a different kind of distribution of wave field. Okay, so if you take into that consideration, you can create a different data set based on that iteration, parareal iterations, like that, using similar approach. And this is just the statistics of the Fourier modes of the training wave field that comes out. This one is the one that I just described to you a few minutes ago, and this one was the one that involves further propagating the wave field involving this particular parareal iterations. Okay. They look different. There are more high frequency components, statistically speaking, from the training examples. And this is the result. And that tells you the importance of training training data set with respect to the operations that you try to do. So this is the waveguide. This is the smoothest of all. This is an inclusion where you have some scattering. This is the British, the BP data set, and this is a. So ignore the black one. The black one is some reference, very stable reference solutions. Kind of like just we want to beat that. The blue curve is the one that's trained without considering the special features of this parareal iteration. See that in the first few iterations, it does quite well. And after you accumulate, the wave will start to look different, significantly different from your training examples. And that's when the errors start to grow. Whereas if you train it with the specially prepared training examples, then you see that the error continues to decrease as the K iterations increases, right? So this is this is kind of the point that in the end, what we think is that, and this is the effect of delta T, which in the interest of time, I'll just skip, and the basic story is unchanged. So this is it, right? So what I've told you is we want to deal with multiscale computation in the situations where certain majority of classical approach fail, and we would like to consider the use of this kind of deep learning to make up the deficiency of more classical methods. Right? Is it possible to do? How do you compare your computation? So this is regarding which norm you want to think about. And in this talk, we think because it's linearity, we make use of that, and we use the wave energy semi-norm in comparing what's good and what's not good, right? But further than that, we describe this particular way of generating this correction operators through data. And in the context of scientific computing, you have the freedom to generate data. So you need to think very carefully what data you want to do. And this is different from analysis, because analysis, you can say that I want to define this operator for a class of continuous functions, or for H1 functions, etc. And then you work on that, and mathematics will lead you there. But here, is it possible to, because you have only limited resource, is it possible to sample the class of continuous function defined on the unit square? At what cost do you want to do it? So some people like to say that this kind of neural network can extract knowledge from data. I think it's more extract certain skill, because people talk about this kind of network. You cannot explain it. You don't know why it does it this way. You can only think why by how it's created. Right? So I would say deriving a skill from data. And we talk about most likely how to set it up in an offline setup. And I show you that if you really, with a neural network, let's say we have good knowledge about certain approximation aspect of this neural network, no problem. But we shouldn't stop there, because the performance depends on how you generate the training data. Okay. And I think maybe I'll just stop here.
So thank you for the interesting talk. So can one, of course, there's a lot of freedom here to choose parameters, the training, the network. But are there certain situations where you understand what the corrected scheme is that you get? Is it a better finite difference scheme that we already know, or is it a new?
So yeah. So one of the challenges, in my view, one of the challenges in trying to use deep learning strategy in solving scientific computing problem is that we know a lot about how to solve this problem PDEs very well. So I would say it's relatively difficult to solve them. So you need to find a situation where you could, a scenario where you can justify that this is indeed worth doing. So therefore, we did, this is why we think about this, right? What do you want to correct? And ideally in the in the viewpoint of correcting or coming up with numerical scheme that has minimal numerical dispersion, you should go spectral. But then, of course, you can say how does a spectral scale in 2D or in 3D? There's this log of Fourier transform that would get you. And there are some people who's anyway. So I don't want to get into the debate of optimality of spectral method, but we can say that assuming that you want to use the best numerical methods in a certain kind of highly resolved grid, because of the challenge that arises from here, it's too costly, and you would like to see whether there's some way to improve this. And furthermore, this is not just one, classical numerical method. Of course, you can say there's one method derived for all kinds of velocities like that. And we would like to say, okay, outside from this, maybe, or we can say, we can take a step back and say that maybe what we want to do is we want to outperform the best classical method for some example, in some sense, similar to this in the neighborhood around that. Yeah. So I wouldn't say that whatever I presented here is like, you have to go out and use it. This is a proof of concept and say that, well, in the setup that I presented, it seems that it's possible to gain some computational speed. The neural network that I presented here is a factor, a couple of times faster than some fully resolved grid. It
was not to diminish what we just it could be interesting to find maybe new schemes. This approach that you could find some things that you already know, but you could also find things that.
Yeah. So I would. Yeah. So for. Yeah, I think that this is one of the scenarios where maybe there is room to find something like that. Or in this kind of situation, in the first example I mentioned, we have fast oscillations that's coming in and out of resonance. Before the resonance one type and out of the resonance one type, but in between it's something that's really murky. But the nice thing is that you know how to analyze those things. And you can try to exploit that. And the other thing is that the neural network itself, such kind of neural network, not particularly this one, but more classical, So this one here, this JNet doesn't have a complete, we don't know completely, we don't know, there's no satisfactory approximation theory about this neural network, this type of neural network, this class of functions yet. But if you think about more classical, like each layer has the same width or whatever, there's a very clear picture of how fine the neural network can approximate what type of functions, right? If you were in last week's talk, there's mention of Barron space, and and how it's related to Sobolev space, and how this scales with the number of unknowns in the parameters, and also how many data points that you need to do. It's there. In a more safe setup, it's completely there. But the boundary is, for example, you think the classical approximation theory, let's say Barron's paper or whatever, mostly tells you that, okay, the data is sampled uniformly in certain space, which is not true in practice. For example, here, if I'm interested in seismic exploration, the initial condition is only certain chirps, certain wavelet forms, and you send it in, and you only care about a wave like this, and then you see that the subsequent wave field is just lower dimensional objects. So in other words, when you really set it up and make it work, your data points, if you do some kind of manifold learning to study the dimensionality of these kind of manifolds, it's much lower than the embedding space. But so in that aspect of approximation theory, in my opinion, there's still some room to give. To go like that. But I think the question, the talk probably coming out of my discussion with Jing Wei, right? So what can you do and what makes sense, right? If you don't do the training, so my personal view is that if you don't do the training data well enough, you're not going to work. It's not going to work. The operator that you try to learn, is fix a C is linear. What could be nicer than that, right? And with a C, it's a nonlinear, but it depends smoothly on C. So, which means that certain classical approximation theory result already applies, but you need to make it happen. But make it happen is the other link, the rest of the things. So the this picture over here? How do you complete the picture? And that's not it either, because you say that you're able to create some operator that minimizes this, but this only sees the data points that you generate. And now you want to apply it to something else. It's like, so how do you do that?
You can eat this time. We
Okay.
should continue probably over cake. Thank you very much.